trying to find your audio thing.
Is that? And the challenge comes out to 1 over root 2, 0, z. Yes, sir?
Is the sign of the coefficient really matter?
What a good question. Does the sign of the coefficient matter? That's to say, if this is the minus sign or if this is the plus sign, does it matter? Right? Why would they say we swear anyway when you pick up the mentioned waveform wave function, you can only measure a probability by doing something a lot of times. So, does that sign matter? Well, if all you're doing is predicting is kind of the probability, then no, the sign does not matter. But wave functions can interact with other wave functions, and in those interactions, the sign here does start to matter. Okay, so in a good number of problems, this sign will not actually affect the answer that you are calculating. But in some problems it will. You cannot ignore it entirely. When we get to some of the more advanced problems, which won't be until after the quiz, of course, then you will see that it really does start to make a difference. Sir?
Are the differences in sign?
Say it one more time?
Are the differences in the sign?
Are there differences in the sign? The reason why they're not needed? No. These are signs, the coefficients of wave functions. The commutation is about operators, which is something else.
But like when you have the wave function, you take a look at the value for like f1 times like the only difference is
right. There are differences in signs, but those differences in signs it's not the same as commuting, not commuting. That's a different origin. The main thing that happens is if you have here, let me take an example. If you have here's an example. So if you look, you have let me just write down two of these. -1 x over 2 alpha. So consider this, right? And then this. Okay, these are just two that I just copied on the book, right? Now, you'll notice that they're like basically the same except for a minus sign, right? So like, what's the difference? Because the probabilities come out the same. Well, that doesn't mean there is no difference, and I'll show you why. Tell me, what does this equal? The bracket of -1x with 1x. It's not a trick question. What does this equal? 0, right? Because these are eigenstates of the same operator. That's what the x means, right? And they're not the same, so they go on to 0, right? So, but that has to happen if you substitute these in too, right? Well, if you do that, if you take the -1 bra, it'll give you this times the -1 times the +1 ket. Okay? Now, you distribute this out, most of them go to 0 as before, so we'll just take the ones that don't. Here's a -1 with a -1. That could be 1/2 times 1/2 sorry, I should probably square it. Oh no, I don't need to square it. Because you -1 times -1, so 1/2 times 1/2 is 1/4. And then -1 over root 2 times +1 over root 2, which gives you minus 1/2, and then plus 1/2 times plus 1/2 gives you plus 1/4. And what does that give you? 0. That's your answer, like it should, like it needs to, right? But notice, why did we get a 0? Because these two had different signs, right? Because these two different signs, you get a minus sign here instead of a plus, and that makes it split a 0. If on the other hand, you do negative 1x with negative 1x, what's that x going to give you? Well, that should be 1, right? Well, if you work it out, you do the exact same thing, except that both of these are minus signs, right? In which case, you get 1/4 plus 1/2 plus 1/4, which equals 1. Okay, so those minus signs do something, right? Even though by themselves they seem like there's no difference, when you combine them with other things, the minus signs make a difference. So that's why we need them. Yes, ma'am.
So like yesterday, you were saying how you guys would give us like these substitution equations and have things that not multiplicated and like giving us enough.
If I Maddie asked what would it be if I didn't just give you the equations, but just give you information about it, what would that information look like? And the answer is it would have to be things like it would have to be something like if the particle is in state negative 1x, then you have a 25% chance of measuring it to be negative 1z, a 50% chance of 0z, and a 25% chance of 1z, right? So that you could reconstruct that equation from information given, right? So that information would not be the minus sign, so that it would have to be something simple. But in principle, I could give you some stuff that allow you to figure out what that equation is, just by giving you probabilities of the outcomes. So that would be something I could do. But I mean, you can see it's not hard, right? Just remember to take the square roots. Are there other questions on the homework? So we have a lot of stuff to do. Yes. Anyway, we've got to get it done. So I'm going to talk for a little bit about one thing that is interesting and worth knowing, and then the rest of the time. Oh, here before I forget, I have a assignment sheet up on Moodle for what I call Election Day, which is the voting that we're going to do on our favorite detectors. And so it says all around there, just to reiterate, each person in your group is responsible for one slide of one subdetector, so including accelerator, right? So accelerator, tracker, calorimeter, muon detector. If there are only 3 of you in the group, then you may just cut it to 3, or if you want, you can do 4 anyway, just to increase your chances of winning, up to you. You don't get extra credit for doing the 4th one. But if you want to, you can. If you want to try and increase your chances, you can. Or you can just leave it in 3 if that's fine. Leave that up to you. So yes, so that's going to happen. Then what's going to happen, I will probably do this offline to try and minimize the class time. I don't know, it's kind of fun to do it in class. I don't know, we'll see. But once I get them from you, I will compile them together. I will then, we will then send like a Google form, and we will vote on it. And then we'll pick the winners, and we will go from there. So, as I said already, one slide, sell it, don't lie. But include, okay, so here's a few things. For all of you, so both in your decisions and in your advertisements help people make their decisions, what do you want to know about someone else's detector?
Its name. Why we should vote for it.
You want to know some numbers, right? Things like resolution or center of mass energy or things like that, luminosity, things like that should be relevant. Most of those numbers you want to be high, right? At the same time, don't go blindly by the numbers. You should consider, so let me tell you this. Last year, I observed that the competition at the Fermilab when the physicists were deciding was quite close. And I think what swung it in favor of the winning team was overall that it was a more innovative approach. So I think innovation certainly counts for something, but bad innovation, let's say, innovating something that makes no sense is probably not necessarily going to help. So I would recommend you not just try to do a boring by the numbers approach. Like we don't want a mindless approach to this. but really, which do you think is the most interesting detector? Also, do not worry about trying to fit them together, because they won't, right? We'll have to make adjustments, and that will be done. In other words, some of you have cylindrical geometry, some of you have spherical geometry, some of you have both, I believe. So so that will have to be fit together later, right? So don't worry about trying to get them to fit together. Just say which of these detectors is like do I think is the best one, right? Okay, so just keep that in mind with your advertisements as well. This is the sort of thing you want to sell to your classmates. Yes.
You said that we get extra points with our current education.
Yep. Yep. The team. The whole team designed it. So yeah.
So, if our like numbers like that we gave to you are wrong, but like we don't know that.
I haven't read anything yet.
Yeah. So.
Then just do your best, right? That's what I do. Also keep in mind, like if you see a number that seems suspicious, you guys all know each other, you know? You're like, did they really do this right? So I will leave that part to you, just as you have to do when you're evaluating the comments made by a politician or something. Yes, Betsy.
Say that we get some notes back and it turns out that we made a really big mistake.
Are you talking about the 770 Tesla?
I'm not going to point anything out.
Something like the 770 Tesla, you're welcome to correct.
Okay.
I mean, that was just a mistake, right? Aside from that, aside from something that's really just a mistake like that, you should not be making, and that was kind of a ridiculous mistake. It's kind of, aside from that though, you should not make any changes to your design, right? Like if it's something like that that's really just a mistake, then fix the mistake, that's cool, right? But anything like, oh, I wish we had done it like this, no changes now. You don't really have time anyway, right? Let's be honest, yeah.
Nobody got time for
let's
that.
not do that now. When you're working on the final detector, then you can make the changes that you need, okay? Good, so let's talk about something interesting.
Oh no.
Oh god.
Remember yesterday?
IMSA students, you're supposed to be happy when I say I talk about something interesting.
It means
Like,
something
we're
different
not
in
saying
ways.
students,
We know that.
Okay, yeah, for example. Okay, so let's talk about community operators. I have to say something briefly about two different types of things we deal with, two different types of numbers we deal with. The type we're focusing on in quantum in this unit is things that are discrete. What does discrete mean? Separate. Good. Separate. I'll give you an example of a set of numbers that is discrete.
18.
Integers, thank you, that's right. Integers are discrete because you have 1, 2, and 3, and between 2 and 3 there are no integers, right? There's a gap there. They are countable and so forth, right? So that's discrete. There are gaps, right? A lot of when we work in quantum mechanics, because the name quanta means count, right? What we deal with in quantum mechanics is usually discrete, or a lot of it is, especially in this class. I've been focusing on that. But there are plenty of things that are not. For example, things like position, as far as we know, is not discrete. Like it's not like you can only be here or here. It's what's the opposite of discrete? Continuous, right? So discrete, there are things like energy, for example, sometimes is discrete, right? Or if you like, grade is discrete. Interesting, including both your grade in school and your like ABCD class grade is also discrete, even though there's no reason why it should be. Why would that be a discrete number? But anyway, I think letter grades are really not much good at that time. Like they're an archaic, really archaic way of grading. It didn't really make sense in the 19th century, but really doesn't make sense now with computers and stuff. So then continuous is things like position or momentum or plenty of other things, right? Are continuous distributions. Right now, when you deal with continuous stuff, the math just gets a little more complicated because of that. I don't go into it a lot because you really need calculus to do it right. But the main thing is that in a continuous distribution, the main thing is a continuous distribution. Like let's say this is position, right? Let's talk about measuring the position of something. when I measure the position of something, let's say I'm measuring the position of an electron, and I'm like, oh, it's right there, right? I have some origin somewhere, and I'm like, it's at x equals 5.3 meters. Okay, so it's at x equals 5.3 meters. But tell me, how well do I know that 5.3 meters?
Well, it's a measurement.
Yeah, well, by default, that's our standard sig fig approach is that I know it's the nearest tenth of a meter, right? I know 5.3 plus or minus 0.1 is how the like, sig fig approach. Right, you guys learned that when you did sig figs? We don't use sig figs because there's no one using them. It's only chemists use them, yeah. I don't know, they like, for a while they like infiltrated physics and then the teachers noticed that we were teaching it, but we never actually used them. And I'm like, hey, wait a minute. So they kicked it back to chemists. Physicists, what they use, they would say 5.3 plus or minus whatever the actual uncertainty is. But here's the thing. Well, could I measure more precisely? Yeah. Sure, I could. Right? Get a better ruler or calipers or whatever system you're measuring the laser size with. You can make it better. But here's the thing. You can measure something more and more precisely, but you can never measure it to perfect precision. If we're talking about something that's a point-like particle, you cannot measure its position to perfect precision, right? So I can measure the position of this thing to the nearest meter, which is not very precise, to the nearest centimeter, right, to the nearest millimeter. I can measure it really well to the nearest micron, right? I can measure it to the nearest, like, picometer, right? So now we're talking about, like, that's within an atom's width. That's pretty good, right? But you can get more precise than that, right? So the point is, there is always, as far as we know, as long as it's continuous, there is always some precision. There is some precision with which you're not sure exactly where it is. So even if I knew the position of this particle down to the diameter of a proton, right? Still, it might be off by the size of the diameter of a proton. You never know it perfectly what its position is. So, because of that, when we talk about collapsing the wave function, right? You say it collapses the thing you just measured. Well, with the measurement of something continuous, it doesn't collapse the thing you just measured. It collapses to, like, a narrow range around you just measured, based on the precision of your measurement. You see what I'm saying? So instead of measuring something perfectly, you measure it down to about that far, and that's what your wave function collapses to. You know it's somewhere in here, you don't know where exactly. Excuse me. Does that make sense? Yeah. Right? So it's not a huge change, it just says this precision. Now, do you know how we measure this precision? Well, when you have a distribution that looks like this, here, I'll draw it a little nicer, just to make it make it wow. Eraser hit. Let's make it a little wider. Do you know how we measure precision? Precision is basically how wide this thing is, right? How do we measure how wide something that looks like this is? Standard what? Standard deviation. You guys remember that? Yeah. Yes. Twitch. All right. So we use standard deviation to measure the precision. Now we don't need to know the mathematical definition of standard deviation. Okay, that is not important for this class, but you should know it still. We learned it in MSI.
That doesn't mean we
And I know you retain every single thing you learned in MSI and every other class ever, right? So, the standard deviation is how you measure the width of this thing, right? Larger standard deviation means what about your precision? Less precise, right? It's a wider standard deviation means you have less idea where the thing is, right? So you want this standard deviation to solve. What is the standard deviation you're measuring really though? This is a wave function we're talking about, right? So it means if you repeat the experiment, actually, what's the letter we usually use for standard deviation? Sigma, right? Use the lowercase sigma like that. So if you repeat the experiment many times, then standard deviation is sigma in your measurement, right? That's what we mean by standard deviation. If you can measure it. Okay. Where are we going with this? Well, let's talk about these two particular continuous operators, position and momentum. So with position and momentum, they're operators. They can be written in operator form. You don't need to know it, but the position operator can be written as x like I said, you don't need to worry about this mathematically. The momentum operator, which kind of makes sense maybe, the momentum operator can be written as h bar over I d by dx, which might make a little less sense to you. Anyway, you don't need to worry about that, like I said. I just say there are forms of these operators, right? Every measurable quantity has an operator that corresponds to. These are the operators of those. But the important thing we discover if we work with them is we find that the position and the momentum operators, got a guess? Do not commute. Position and momentum operators do not commute. What does that mean? That means you can't know both of them at the same time. But you know, as I mentioned, with position or with any continuous operator, you never know it, right? What it really means is there's a limit to how well you can know them simultaneously, right? You can know them kind of simultaneously, but there's a limit to how well you can know them both. That limit can be expressed mathematically, and the mathematical expression is one of the famous parts of quantum mechanics, which is called the Heisenberg uncertainty principle. Okay. The Heisenberg uncertainty principle is just the mathematical statement of what means that position and momentum doesn't commute. It tells you exactly how much can we not know them simultaneously. And the way you write that is like this. This is the Heisenberg uncertainty principle. Sigma x, times sigma p is greater than or equal to h bar over 2. I need to define h bar for you. H bar is a variable we use a lot in quantum mechanics. It's equal to h over 2 pi. And you're like, well then why don't we just say h over 2 pi? It's not that hard. Well, the reason is, look, h was found a long time ago before we knew the slightest thing about quantum mechanics, right? As we learn more about quantum mechanics, we discover that the thing that Planck found was not quite a fundamental quantity. It was close, but it was not actually the fundamental quantity. It was off by a factor of 2 pi. So we use h bar actually all the time because h bar is actually the fundamental quantity for the thing we're talking about. Okay, and we'll see as we go further into quantum mechanics why h bar is such a fundamental number. No, they just switched. No, they just switched to a new one. I mean, it was just. Okay, so we use h bar all the time. It's pronounced h bar. It's an h with a slash to it. Yes.
You ever has science ever changed like what particular term means? Like,
yeah, I mean it happens naturally over time. You go back and read stuff by Newton or something, it's almost indecipherable. Even in Latin. But I mean, even if it's translated into English, used with very different vocabulary than we use now. Some words like force are still there. There are a lot of other words that are not. Right? So yeah, things definitely change over time. Science papers from 100 years ago, a lot of them are almost stupidly meaningless. Like they use just a lot of concepts that we just don't use anymore. They have a very different approach to things that we use now. So yeah, the language of science definitely changed over time with all of the language. Okay, so this is the Heisenberg uncertainty principle, and it's important to talk about what it means, right? What does it mean? Well, sigma x, right, is the standard deviation of many position measurements, and sigma p is the standard deviation of many momentum measurements. So what it's saying is that there is a limit to how precise these can be simultaneously. Okay? Now, notice that it is possible for sigma x to be just as small as you want. Right? But if sigma x gets really, really small, what will have to happen? Sigma p will have to start getting bigger. Right? It's a requirement. And if sigma p gets really, really small, sigma x will have to get bigger. So if you have some measurement apparatus that measures the position extremely well, that's cool. But then what happens as a result? When you measure the position, the momentum of the particle becomes very poorly known, right? Or you say, okay, now I run through an apparatus that measures the momentum really, really well. So what's going to happen? Sure, you can measure the momentum really well, but now the position is not well known. Okay? I recommend not using any of the analogies that popular science writers have given. The analogies are all wrong. There are no analogies of this in the real world, the regular world, right? We do not experience anything like this. Okay? So I recommend not to try to make sense of it in that sense, because the analogy will break down, usually pretty quickly. Rather, it's better to say what we know, which is, if I measure the position, then to a very precise level, then my knowledge of momentum is unknown. And if I measure the momentum, or is very poorly known. And if I measure the momentum to a very precise level, the knowledge of position is very poorly known. And that's it. You're like, what does that look like? It doesn't look like anything. These are electrons, you know? So it's just a statement. This is, as far as we know, what is true.
I was going to say, if you had a device that measured momentum really well and a device that measured position really well, wouldn't it be able to measure?
Yeah, well, you could do either of them in order, but whenever you do one measurement, it collapses the wave function, right? So when you make your position measurement, the momentum becomes poorly measured. When you make your momentum measurement, now you've got your momentum, but the position is no longer well known.
But at one point you can do it simultaneous,
No,
can't
you
you?
can't.
Why not?
Because you can't do things simultaneous. That's a funny word, simultaneous, don't you think?
Yes, I know it's a funny word, but
no, we have no,
There's
there
always
is no
one reference frame or
mechanism
something
by
that
which you
can
measure a
simultaneously.
particle
No,
momentum and
there
position
has to be
simultaneously that we can
Remember, it
follow.
has to be
You really just get one of them at a time.
You can, but the distance between the two would have to be practically massive.
So it's so this is the hyperconcerted principle. Here's the main thing. A lot of you probably heard of this before. A lot of arguments given about the uncertainty principle are based off our measurement ability. Oh yeah, well to measure something you have to hit it with a photon, and in order to do it, it makes it sound like we are not smart enough to figure out what the position of momentum is. That is not the case. This is a fundamental, so far as we know, quantum mechanical effect. That is to say, there is a fundamental limit on the knowledge of, and it's not even on the knowledge of the position, it's on the position itself, right? If you have not measured the position to more than this, then that position is not determined, right? It's not known. It is not a fixed position. So you cannot say, oh, it's really right here, but we're not smart enough to figure out. This is quantum mechanics. It's not really anywhere, right? It's somewhere in here. And so this is a fundamental limit on knowledge, right, on the position of the particle itself. It has nothing to do with how good our tools are. It is only about the universe itself. This number is calculated directly from a wave function, right? You can calculate it. It's nothing to do with your tools, nothing to do with your measurement devices. It is just, it cannot be known past this level of precision. Okay? In exactly the same way as we talked about the non-computing operators yesterday, right? It is just a continuous version of that, so you can write it out in this mathematical form.
Yes.
Yes.
So are there like other quantities that like you
Are there other quantities that form something like this? Yes. Are any of them interesting? Not really. Yeah.
Just lost my train of thought, sorry.
Okay. What's the spot sound? 25? Okay. I have what I have for preparation for Monday's quiz. By the way, the other class said you were all stupid. I want to let you know that.
What?
I told them that you guys had voted and decided you'd rather have Monday, and they said you were all stupid.
Oh.
Just like my parents.
And I said, well, there was, what? No, they applied to you because I said there was a substantial enough majority that other class is especially smaller, so they would. I was like, you would, even if you all voted the other way, it wouldn't be enough that way. They're like, well, then they're all stupid. That's what they said. Well, all right, just letting you know.
Well, they're stupid.
There we go. I'll tell them you said that. So that note says, you're stupid. I know you are, but I'm not. So, all right, we'll be sure to tell them. Don't worry. Okay. So here's what I have for you that you should use in preparation for Monday's test. There is that document on direct notation that you should probably go over. I mean, it's probably worth going over again. There's homework 20 and homework 21 are the essential ones, right? Remember, the test will not be on photoelectric effect or interference or anything. It'll just be on this like formalism stuff with the rods and kets and the measurements and the eigenstates and all that. Okay. So homeworks 20 and 21 are crucial. I posted a problem, a practice problem on the practice section on Moodle, which is also good test practice. It's not super hard, but it's good. I mean, it's not like level 3 level, but maybe level 2 level or something. To get you can get accustomed to what's going on. I know we have a lot of stuff going on. I am sorry for this crunch. I do not like it this way. I have not been able to figure out another way to do it. So sorry for that. It'll be a lot easier in December. That's all I can say. And so anyway, I want you to go through this. So those are the things you can go through, that you should go through in preparation for Monday's test. And I recommend you do so. You have a question?
Yeah, are we going to be taking our like?
Yeah, we do quizzes in here now. We've dropped a few people, and so we just fit in here with difficulty. So I think we'll do that for now.
At least they're dropping meant something good.
What?
At least them dropping that have some benefits in the class.
Mm-hmm. I mean, it does. Also because we had some drops now formula that can fit us. Further, like, no, that's way too many. I'm like, okay. And she's like, what's the updated number I get? And she's like, oh, now it's not. Yeah, it is, but okay, sure.
Way too many.
Yeah, right. Yeah, it's like 3 too many. Okay, sure. Okay, so I want you the rest of the time to work so that you can ask me questions and stuff. Work on whatever you need to work on.
Yeah, we need to increase resolution.
Alrighty. What? I can't hear you. So I still need to run the Tesla calculations to see what a magnetic strength needs to be of a magnet. And when I do that, I'll be able to calculate how big the thing is.
Again? Okay.
After that, it should be
Not
fairly
gonna
simple.
complain about that.
It's just the
You actually
magnetic
lost that
calculations
stuff?
are a pain in the butt. You
Really?
the document that I sent you with the equation on it.
Wait, it's still on? Oh my gosh, that's like really old.
Yes. Can you send that to me? Or resend that back to me? Because that had a way for me just to